This is AS Chemistry Chapter 6, Lesson 1 on reversible reactions. So let's start by talking about what a reversible reaction is. In some reactions, the products can react to make the original reactants. And these reactions are called reversible reactions. And because a reversible reaction goes in both directions, so forwards and backwards, we'll use two arrows, and the symbol of the arrows can be seen there, instead of a single forward arrow. So there is our reaction. It's just a generic reaction, so A plus B. There's the symbol in red for the reversible reaction, which are two arrows, which I'll talk more about in a minute, and the products are C and D. And what's very, very important to make sure you understand is that normal reactions that are not reversible, will go from reactants and turn into products. And there'll be a single arrow. And that means that the reactants react together, turn into products, and then that's the reaction. And once the reactants, or one of the reactants gets used up, the reaction will come to an end. A reaction that is reversible, what it means is that the reactants can turn into products, and the products can also go back to the reactants. Some reactions will be reversible at room temperature, i.e. they will go from reactants into products and products into reactants. And other reactions will be reversible in the way that the forward reaction will take place, and then you might have to heat it up, but then the backward reaction will take place. So you can go from products to reactants again. And we'll look at some examples in a minute. But what we're interested in is that a reversible reaction is where the products of a reaction can react and they can reform the original reactants. So reactants turn into products and products can form back the reactants again. And what we need is an arrow, or we have two arrows, one showing that the reaction goes forwards and the other one showing the reaction goes backwards. And make sure you can draw the reversible arrow sign. So a reversible reaction can go from reactants to products, and products can turn back into the reactants as well. And that's what a reversible reaction is. And that's a symbol for a reversible reaction. Let's look at some reversible reactions. Some of these reversible reactions you may have seen at GCSE. And this is a very popular reversible reaction. And it involves copper sulfate crystals. Blue copper 2 sulfate crystals contain water and are called hydrated. And that's what they look like. So blue copper 2 sulfates contain what we say water of crystallization. And the formula of blue copper 2 sulfate is CuSO4.5H2O. And because they've got water of crystallization, it means that they are hydrated. So these are hydrated crystals. When these blue crystals of copper 2 sulfate are heated, so they're heated quite strongly with a Bunsen burner, the water will evaporate. And as the water evaporates, they turn white. So they become dehydrated. Okay, so they lose that water of crystallization. And what we say is that this produces anhydrous, without water, copper 2 sulfate crystals, which are now white. So they look like that. So blue copper 2 sulfate is heated strongly and it turns into white copper 2 sulfate, and the water becomes evaporated. The water is lost by evaporation. And here is an equation for the reaction. So CuSO4.5H2O is blue hydrated copper 2 sulfate, and just CuSO4 by itself is white anhydrous copper 2 sulfate. And what it means is anhydrous means that there is no water, and hydrated means that water is present. And we can clearly see the difference between the blue solid on the left and the white solid on the right by looking at its formula. So the blue solid has water associated with it and the white solid doesn't. But what's very, very important to understand from this slide is that when we take the blue solid and we heat it strongly, the water evaporates and the solid turns white. And there's the equation below. CuSO4.5H2O, reversible sign, and that's what I'll talk about in a minute. Again, the next slide turns into CuSO4 plus 5H2O, and that equation is balanced. What we can then do is we can pour water, either water that we've collected, if we've managed to collect it by some mechanism, or we can just take water from the sink. We can add water back to the white anhydrous copper 2 sulfate, and it turns back to a blue colour. It forms the blue hydrated copper 2 sulfate again. And there is a picture of the white anhydrous copper 2 sulfate, and when water is being poured onto it, we can see that it turns into blue hydrated copper 2 sulfate. And this is a useful test to show that the liquid we have is water. Okay, so this colour change is a useful test for water. So again, when we take the white solid that we've got and we pour the water back on, and that's where this equation represents the plus 5H2O, it turns back into the blue colour. Now what's very, very important to understand is that this is a reversible reaction, because when you heat it strongly, i.e. it's an endothermic reaction, so you heat the blue solid up, the blue copper 2 sulfate, which is hydrated, the water evaporates and it turns into this white powder. When you add water to this white powder, it turns back into the blue solid that you initially had. And then you can heat that blue solid up again, evaporate the water and turn it into the white solid. You can collect that water, pour it back onto the white solid, and it will turn blue again. And that's a reversible reaction, because the reaction just goes forwards, it then goes backwards, it goes forwards, and then it goes backwards. Now what's very, very important with certainly this topic, which we're looking at reversible reactions, is that to understand that if the forward reaction is endothermic, and endothermic means that you have to put heat energy in order for the reaction to take place. So heat energy is taken in. Well, if the forward reaction is endothermic, then the backward reaction is the opposite. So the backward reaction is exothermic, i.e. that the backward reaction gives out heat energy. So the forward reaction, if it's endothermic, if it takes in heat energy, means that the backward reaction will be the opposite. In this case, exothermic, and it gives out heat energy. But the key message from this slide is that this is a classic example of a reversible reaction, one that the reactants turn into the products, and then the products can turn back into the reactants as well. So it's a reversible reaction which takes place. Okay, let's look at another reversible reaction that you may have come across, and that involves using ammonium chloride, which is NH4Cl. When ammonium chloride is heated, again a reversible reaction takes place. If ammonium chloride is heated in a test tube, the white crystals of ammonium chloride disappear and they appear further up the test tube. And if you look carefully at the picture at the bottom, you can see that the Bunsen burner flame, i.e. the blue flame, is strongly heating the white crystals at the bottom, and that's the crystals of ammonium chloride. And as they're heated strongly, you can see that they disappear. That's why you've got the colourless gap between the white solid at the bottom and the white solid that's further up. If you look carefully, you'll see white solid, a gap, and then the white solid again. And what's happened is that the ammonium chloride has been heated, it disappears. We'll talk about why it disappears in a minute, and it reappears further up the tube. And what this shows us is that this reaction is reversible. Now what's very, very important to understand is what's actually happening. What does the ammonium chloride turn into when it decomposes? So this is a decomposition reaction, a reaction where the ammonium chloride breaks down. So when ammonium chloride is heated strongly, it decomposes into two colourless gases, ammonia, NH3, and hydrogen chloride, which is HCl. So ammonium chloride decomposes when it's heated strongly into two colourless gases, ammonia and hydrogen chloride. So at the bottom of the test tube, you've got the ammonium chloride, the NH4Cl. When you heat it strongly with the Bunsen burner, it decomposes into ammonia and hydrogen chloride, giving us that colourless gap that we can see at the bottom of that test tube. So that colourless gap is a mixture of the two gases, ammonia and hydrogen chloride. Okay, and again, here are some more images, but the image at the top, we can clearly see that colourless gap, which is of ammonia and hydrogen chloride. But we also pointed out that the white solid reappears further up. So clearly what that tells us is that the ammonia and the hydrogen chloride combine back together and they form ammonium chloride again. And that shows us that this reaction is reversible. So the colourless gases rise and they cool up as they travel up the test tube. And as they rise and they cool, they combine back together and they form ammonium chloride again. So the two colourless gases, as they cool, they'll react together and they reform ammonium chloride. And this is a classic example of a reversible reaction. The white solid is heated, it turns into the colourless gases ammonia and hydrogen chloride. As the gases cool, they react back together to reform white crystals of ammonium chloride. So the reaction goes forwards and then it goes backwards. So it's a reversible reaction taking place. And again, this is just a diagram taken from a GCSE paper where it clearly shows you the ammonium chloride at the bottom, the ammonium chloride at the top, and the colourless gases, which is mixture A, in between. But it's a reversible reaction, one that can go both ways. Okay, now let's move away from these examples of reversible reactions and look at this term, which is dynamic equilibrium, and understand what dynamic equilibrium is. Many chemical reactions are reversible and have a tendency to come to equilibrium. And we'll talk about what equilibrium is in a minute. The symbol that we've already been talking about, which are these two arrows, that means that the reaction is reversible. But what does this term equilibrium or dynamic equilibrium mean? I'm going to start by looking at the definition of dynamic equilibrium, and then we'll briefly look at one example. And in the lessons to come, we'll certainly look at this term dynamic equilibrium and the term equilibrium again, because that's what this section forms. And it's essentially how equilibrium is affected by changing conditions. So we'll look at more and more about that later on. So I'm only going to briefly introduce it here. The definition of dynamic equilibrium is the following. And there's two features of a reaction at dynamic equilibrium. So the definition is, at dynamic equilibrium, both the forward and the backward reaction is occurring at the same rate. So at dynamic equilibrium, both the forward and the backward reaction is occurring at the same rate. The concentration of reactants and products remains constant. So the concentration of reactants and products remains constant. If you are asked in the exam to write a definition of dynamic equilibrium, you must state both of those points, not just one, both of those 2 points to get 2 marks. Sometimes the question will say a reaction is in dynamic equilibrium. List 2 features or suggest 2 features or state 2 features, any of those terms, state 2 features of a reaction at dynamic equilibrium. Feature 1 is that both the forward and the backward reaction occurs at the same rate. Feature 2 is that the concentration of reactants and products remains constant, and that will secure you your marks in the exam. So make sure you learn the definition and make sure that if they ask you for the features, you can state them. Here is an example which is at dynamic equilibrium, and again we'll talk more about this reaction in the lessons to come, so I'm not going to worry about too much about what each of those chemicals are and actually what is exactly each of the colours, which you'll expect to know for the exam as well. But here is a reaction which is NO2, which is an equilibrium with N2O4. Now what the equation shows us, which is balanced, we're just going to try and understand what the equation shows us. We've got 2 gases, NO2 and N2O4, and the reaction is reversible. That tells me that NO2 can react, let's just say, with another NO2 molecule and form N2O4. And N2O4 can break down back to NO2. But basically, the reactants turn into the products and the product turns into the reactant. This reaction is at dynamic equilibrium, which means that both the forward reaction and the backward reaction is occurring at the same rate. So if I was to get a glass container and I put some NO2 and N2O4 and sealed it, then this reaction would keep going back and forth. I don't need to heat it to get the backward reaction to kick in. All I will do is put it into a container. So put some NO2, say, into a container, and some NO2 will break down into N2O4, and that the NO2 will form N2O4, and the N2O4 will break down into NO2. So if I had a glass container with some NO2 put into it, it would break down, it would react to form N2O4. The N2O4, once it's formed, will break down to form NO2. The NO2 will again react with another NO2 to make N2O4. The N2O4 will break down. This reaction will constantly be happening. And that's what a reaction at equilibrium is. It's a reaction that is both going forwards and backwards at the same time. That's a reaction at equilibrium. Okay, so we don't need to heat it to get the backward reaction to occur, just like we've seen. It's a reversible reaction, but this reaction is at equilibrium. That's the term we need to understand. That if you had a container and you were to seal it, the forward and the backward reaction will be taking place. So you'd go from reactants to products, products to reactants in that container at that same time. And at dynamic equilibrium, the rate of the forward and the backward reaction is the same. And it's understanding that word, the rate, the speed of the forward and backward reaction is the same, and the concentration of reactants and products remains the same. So a reaction at equilibrium is going both in the forwards direction and the backward direction at the same time. Another classic example is the Haber process. Nitrogen and hydrogen react to form ammonia. That reaction is reversible, but it's also in equilibrium. As the nitrogen and the hydrogen react together, they form ammonia. The ammonia can decompose and produce nitrogen and hydrogen again. And in the Haber process, again, which we'll talk about later on, we have the problem to make sure that we remove the ammonia as soon as it's formed before it gets a chance to break down, because the reaction is in equilibrium. It's going both forwards and backwards. So just before I conclude this lesson, make sure you understand that a reversible reaction means that the reaction can go back in the forward direction and the backward direction. That's what a reversible reaction is. A reaction at equilibrium means that the rate of the forward reaction and the rate of the backward reaction is the same, i.e. the reaction is both going forwards and backwards, and the speed at which it's going from reactants to products to products to reactants is the same, and that reaction is going constantly back and forth. And that's the difference between reversible and equilibrium. This concludes the lesson on reversible reactions. Lesson 2 will look at equilibria and Le Chatelier's principle.